All right, so this is an interactive panel. This is one of two we're going to do. So first of all, thanks everybody for coming. This panel is titled Systems Programming in 2014 and Beyond. And so obviously, if you look at our great panel here, we have you learned a lot today about C++, Rust, and Go. Andre hasn't talked about D yet, but that's also a systems programming language, compiles to native code, blah, blah, blah. So I don't know if we should do introductions, but why not? Let's really quickly do introductions.
Who do you want me to introduce?
Introduce Go.
There's Rob Pike. I remember when he came to Bell Labs, we even shared an office for about 3 months. And he's been doing great things at Bell Labs and then Lucent and then went to the West Coast, did a lot of good stuff with Google. And he was physicist, I remember. Was it Caltech?
Yes.
Thanks. Now, who do you want to introduce?
Okay. Well, this is Bjarne Strustrup. He's a designer and inventor of C++ for Bell Labs, AT&T Bell Labs, and many other things besides. And he's managed to stick with C++ now for how many years have you been working on the committee? No, too many, which is an admirable achievement in and of itself. So. And you can introduce.
I think to be very honest, I need to introduce myself because otherwise nobody's gonna. Well, let me introduce the competition. Rust is a language that we're going to steal a lot from. Inspiration. What did I say? Gonna get a lot of inspiration from, and I actually don't know much about you. So, but maybe you. I mean, I don't know. I came unprepared to this, so maybe you can introduce him.
Watch me bungle your name now.
Yeah.
So I believe you're Alexei Andreescu.
That's very close, yeah.
Okay. And he's I guess, would you call yourself a co-designer of D at this point, or recent designer? Advocate for D, working at Facebook for a few years. And like, I think every Romanian I've met in the last few years, he wears shorts all the time, as far as I can tell.
I'm going to spend the rest of the evening trying to hide my legs here.
And so being an interactive panel, the idea is you guys, drive questions. There weren't a lot of questions today. I realize people are probably shy or whatever. Remove that mask. Ask questions to people who will know the answers in the context of system programming or whatever you want to know about their specific languages. But the first question I want to ask is, what is the systems programming language?
Could you just introduce him properly?
Oh, hey, my bad. Rust. So obviously I know who you are. You're Nico Matsakis. Right on. He is a researcher at Mozilla and currently working on the D programming language or the Rust programming language. Well, I mean, that's going to be kind of a fun thing to talk about. There's some really interesting connections. But and Rust is all about type safe, memory safe, without losing performance at a certain level of abstraction. Just like C++ gives you the power of hardware at nice levels of abstraction, but you don't lose performance. That seems to be the whole thing with systems programming languages, which brings us to the question of what is a systems programming language in 2014? C++ is used for much more than writing operating systems. D isn't used for writing operating systems. It could be. Go isn't used for writing operating systems. They're all system programming languages. Rust, what are you going to do? So that's the question. What is the systems programming language in 2014?
That's a really broad question, but I think it's a really important one because it seems like many people use the words somewhat differently, right? So from our point of view, I mean, the thing that we're most interested in, certainly, in the most selfish point of view, is writing kind of client-side applications, right? So sort of the polar opposite of what Go was designed for example. And in these kind of applications, you have high latency needs, you have high security requirements, you have a lot of requirements that I think don't necessarily come up on the server side. Though I feel like, basically I think that the definition is quite broad. And I would like to think that most of basically that all these languages can be used to some extent in all these domains. I'm sure you could write great client-side things in Go as well, for example. And I'm quite sure you could write good server-side stuff in Rust. So it's probably more at the edges where you'll see the differences, like the extreme cases of each of the different domains and so on. I don't know who wants to answer.
Oh, okay. I think that, systems programming came out of the fields where you had to deal with hardware, and then the applications became more complicated, so you need to deal with complexity. I think if you have any issues of significant resource constraints, you are in the systems programming domain. If you need finer grain control, you will also be in the systems programming domain. And if you are part of a system where part of the system has those concerns, a systems programming language has advantages. That is, you can do a lot of programming in just about any language. It's the constraints that determines whether it's systems programming. Are you running out of memory? Are you running out of time? Are you running out of real time? Are you running out of file handles? And then finally, there's the aspect of actually touching hardware, device drivers, memory managers, and such. But it's like asking me to define play or game. There's something obviously is there, and then by analogy, a lot of other things are there. Don't expect a crisp definition.
No, all right. When we first announced Go, we called it a systems programming language, and I slightly regret that because a lot of people assumed that meant it was an operating systems writing language, and what we should have called it was a server writing language, which was what we really thought of it as. As I said in the talk before, in the questions, it's turned out to be more generally useful than that. Excuse me. But now what I understand is that what we have is a cloud infrastructure language, because what we used to call servers are now called cloud infrastructure. And so another definition of systems programming is the stuff that runs in the cloud.
Thanks. I'm very glad I let Rob speak right now, because my next question was Go introduced itself as a systems programming language, and then that disappeared from the website. What's the deal with that? So he kind of, he was way ahead of me by preempting that possible question. I don't know. It's a broad question. It's a fuzzy, what's a system, etc. And it's what's there and what's not. And it gets into philosophy, and we get crazy before the hour ends, right? But I do have a few litmus tests for checking whether something is a systems programming language. And I think there's a simple litmus test which says systems programming language must be able to allow you to write its own memory allocator in it. It shouldn't escape into another language to do so. And it should be able to forge a number into a pointer, because that's how hardware works. This is kind of two litmus tests that are relatively simple. The memory allocation thing is quite a lot more subtle than most people think it is, because for most higher level languages, completely a kind of a solved issue. It's like language designer kind of toils over a good memory allocation strategy. But for a language in which you need to implement this as well as use it, it's a very solved problem, because at some point there's going to be a point at which a pointer that looks like typed becomes untyped and reused for possibly another type. And all of this kind of manipulation is very contrary to the kind of type systems that high-level language espouse. So it's quite a hard problem, and there's papers on what are the good primitives for such a thing. But ultimately, fundamentally, forging pointers and making pointers look of changing the type of a pointer in flight. I think these are kind of fundamental issues for a systems programming language.
It's interesting you mentioned that, because we're almost completed our rewrite of the Go memory allocator into Go from C. So I guess we passed that one anyway.
So you are a systems programmer.
I guess we are.
I would change your website.
Yeah, change the website back.
All right, so of course.
A slightly philosophical topic here. If you look up systems programming in the Wikipedia, you'll find that it's defined roughly as writing the lowest level of device drivers and is basically useless. It is very tricky when somebody else defines your terms for you. And I mentioned it with C++, with object-oriented programming. We have an example here with systems programming being defined out of existence. And the other example that I remember was Simula, the language Simula that introduced object-oriented programming to the world and got classes and class hierarchies in place, was called Simula. And I met a lot of people who says, no, it was a special purpose language for simulations. There's nothing interesting there. So let's try and define what we're doing a little bit better.
Great. So I'm going to walk around the mic so that you can be recorded and people can hear you.
So I think one of the central challenges of our time is being able to write secure and robust, reliable code. And there's a lot of challenges in that because I think it requires cooperation from the platform as well as from the language. And I'm wondering if you see any interesting paths for innovation from the language space, from systems languages, to support writing more secure and robust code.
Well, yes, I do, in short. But I think, that's we could start by defining what secure and robust and everything else mean. And for me, it's there's the base level of security, which is kind of the properties I was talking about, data race freedom, memory safety, and so forth. And you can argue about exactly which one should be in that list, but there's a kind of basic set of things that you would like to get from your language most of the time, at least. And that gives you a good feeling, and it gives you much more reliable software, but there's another level of robustness above that, right? It doesn't tell you that your program is doing the right thing. It just tells you it's not doing this categories of wrong things. And so what I would like to see, and I hope to see with Rust as we evolve, is people taking advantage of the type system to go beyond the properties that I've talked about so far, to go beyond those basic correctness properties and prove stronger things, like express stronger invariance about their software, which lets you basically get a bigger grain of confidence. I think the simplest, everybody knows that when you write something with a static type system, it's somewhat easier to refactor it, I think. Well, it's certainly easier to do it in an automated way and to get developer tools. It's also easier to find out where is this function used and so forth. And I think we can use similar techniques to say, guarantee, trying to come up with a really crisp example, but guarantee that, tainted data that comes from the network is always sanitized before it gets consumed by a routine and things like that. Those kind of more extended properties that are really semantic and specific to your application. They may not be something that the language chooses to model directly, but being able to model and check that kind of thing seems to me to be very important, and I hope we can see progress in that way.
Yeah, I think we have to distinguish sharply between type safety and security. There are people who go around talking as if type safety was security. Security is a system property. If I'm going to steal your data, I would probably not try and break in to your computer first. I would try and steal your computer first. And then I would do it in my own good time. That's a bit harder with server farms, but still. The point is that it's a system property. I think type safety is the ideal, and I think it has more or less always been the ideal. It's just it's hard to get to. We have to do runtime checks on sizes of arrays, or we have that overflow problem that's easily exploited, either to crash the system or to the security, or we have resource problems and such. So it's the ideal, and just because we can't get there 100% doesn't mean we have lost. And just in the languages where you can get there 100% doesn't mean they've won. It's a spectrum. And we want to use the techniques, as Nico said, of type system and also further analysis to get better systems, but don't underestimate this problem. I don't think you did. I don't think a lot of people here do, but I hear a lot of overly simplified concerns about safety and security.
One of the last ones. All right. You know, it's best to be last, right? Okay, I'd like to make a sort of a dear leader North Korean prediction here. The luminous path is ahead of us. Well, it seems to me, I think I'm going to answer the sort of the larger question. Rust and other languages have a few interesting ideas, but I think they're all part of a sort of a local optimum we're dwelling in right now. I think the entire PL community is in a sort of a local optimum of sorts. I've witnessed this what I'm saying by this is the things we can prove automatically and easily are not super interesting. They're good, they're not super interesting, and the kinds of types that we know how to do are practically very hard to do, such as array bounds checking, eliminating most of these and making them unimmeasurable. So we know how to do it. It's just practically kind of onerous sometimes. So I feel we're at a local minimum. I know this from other communities. They've been stuck in local minima for years. Speech recognition, I've been doing a lot of research, and I left that community exactly when it was on the brink of a huge breakthrough, Siri being sort of part of what came out of it. But essentially, the way I see it, we're ripe for a sort of a real breakthrough in the area when programs are going to be typed in ways that at the same time are interesting, prove a lot of facts, but don't require a lot of program annotations. Where they're going to come from, I'm not sure, but it looks like things are there's some convergence of something going on. This is my intuition right now.
I think that, while I agree we're kind of stuck in a rut, I can see a way out of it because I think that quality of tooling, static analysis and otherwise, that's building up around programming languages in general now is pretty exciting. And I don't just mean like IDEs, although some of those are getting pretty amazing, but the computers are big enough and fast enough now that we can afford to do calculations that would have been prohibitive a generation ago because they would have taken too long. I mean, the resources you spend on whole program optimization, you could direct in other ways. And I have seen some pretty powerful static analysis stuff for safety checks a long time ago now, and which would make it even more practical today. In the Plan 9 kernel, which was written in C, we had all these locking primitives for making sure that data structures were protected properly and so on. And Gerard Holtzman had what he called a protocol analyzer, and he made a version of it that could pick up C code and recognize the calls into the library that we were using to set mutexes and things like that. And it wasn't formally proved, but he sort of dynamically on static code proved that the kernel was lock-free in this case. And that's a very small example, but that was also 15 years ago now. So I think that we're just starting to scratch the surface of what some of these tools are going to be able to prove about our programs, either probabilistically or rigorously.
Great. I forgot to say something. It's not related. It's not a response to this. I was just meant to say that because the question was what's the role of systems programming languages. I think they put great upward pressure on pretty much everything because there is a domain in which no speed is enough, and the more speed you got, the better it is, and safety is good to have given all the speed. So I think the pressure there the pressure put by systems programming language is very practical upwards against the PL research community. I think it's a good thing. Thank you.
And then I'll just take the opportunity to second what Rob said about static analysis. We can do amazing things today. And I think the richer the type system, the richer the analysis that you can get. One of the criticisms of static typing has been that they only catch trivial things. That's because they look at trivial type systems.
All right. Dave?
Thank you. Well, I've been hoping to ask the question that would get all of you fighting amongst yourselves, but this probably isn't it. As cycles have gotten cheaper, we're doing a lot more static analysis, putting a lot more things in the compiler, hoping to get better error messages. But with all of these languages, and Go may be the least bad, I feel like I have to carry a lot of things in my head when I use them. For example, with Rust and the sharing model, I have to think about who I want to share the reference, and do I want to loan it or give it, and do it mutably or not. And with C++, I suspect there's a fair amount. You all are so good and so smart that you carry these things in your head effortlessly, I think. I don't know D well enough to throw a dart at it, and I don't quite know Go that well to do that either. But I think you've tried to minimize it for Go because it's explicitly not for people like yourself. But do you think this is an interesting way to think about the languages? Am I way off base? Do you think your languages do make you carry a lot in your head? A lot of the time I've got all this text, but there's really a picture I'm trying to carry in my head. And it seems very left-brainist, this world of programming languages. So discuss. Thank you.
I think this one deserves to be on my plate. One of the reasons that the languages are so complicated is they carry a lot of history with them. It is really, really hard to simplify a language. The users always want a simpler language with a few extra features. And I may not have been quite as rigorous as Rob mentioned about rejecting features, but I've certainly rejected features up in the high 90% of their requests. And C++ is humongous, obviously too large. And it has 40 years of history with it, starting with C in 72. There are features that just should never have been there, and there's features that should have been there and has been superseded, but they're still there because whatever else we do to our languages, the users do not want their code to change. One thing that I hope for is not just code analysis, I want code transformation. And I want it to, maybe I can finally get modernization of code, code rejuvenation, or whatever you call it, that's mechanically helped. So we can get some of these things that are in C++ just because Dennis had a bad day in the early 70s. And Dennis would agree with me, and actually has. He can't be here to defend himself, but he's not being attacked. All I'm saying is that C was a stroke of genius. I said this morning. I praised it. And some of the details were not right. And you can say that about lots of the features I have added to C++. I could do it better today. I mean, templates would have been half the size if I was doing them today. Now, code analysis, code transformation can help here. Furthermore, I have many times seen the glee when people come with a new language. Look, it's so beautiful, it's so simple, it is not as ugly as C++. Look, to play a guy from a Java world, here is the ARM ripping out 2/3 of the pages saying this is what we don't need. We can get Java, it's beautiful, it's clean, it's assigned from first principle, and it has C syntax. Anyway, so the point is, with age comes all of these barnacles that hangs off the ship. And till now, I have not seen a solution to that. The only languages that doesn't have this problem tend to be languages that didn't survive. C# and Java has doubled in size, tripled in size, and their specifications is about the size of C++. I hope code transformation will help us in this game.
I want to see what you design when you start out fresh.
Since I suspect most of you don't know Go very well, I should probably, on that topic of code transformation, mention something that we did. Excuse me. We were coming up to what we knew would be the first version of Go, which is going to be, it's what we have now, Go 1.0. The point releases since then have all been performance and implementation changes in library. But the language is the same. But we knew we were going to lock it down, and we wanted to get it right. But the problem was we wanted to change a bunch of stuff. We wanted to clean up, delete some features, simplify some features, fix some libraries, get rid of some, I think get rid of a keyword even, clean up things. The problem is, how do you do that without breaking our users' code? Now, we didn't have nearly as many, we still don't have nearly as many users as say, C++ does, but there are people we didn't want to bother. So what we did was we wrote a program called GoFix that could parse both the old and the new things. It had these little modules that glued into it. And it would take your old style program, pick it up, parse it, take the AST, fix it with the module, and then write it out in the new form. And we did some pretty fundamental changes to the language. And the way it was designed to be idempotent, so if your program was already converted, the module had already run on your code, didn't have to run again. And then with each release leading up to Go 1, we just said run GoFix on your code and it'll be fine. And one of the things that made that possible was this amazing library, fundamentally, that Robert wrote called GoFumped, which will take an AST and print it out in human-readable, neatly standardized, formatted output, which some people say is the best feature of the language, and they may be right. But the thing is, this meant that we could rewrite your programs and write them out again the way they were supposed to look, and the way they probably looked before, to be honest. But this had an amazing freeing effect on us, because we were able to consider every single detail of the language, and if it didn't feel right, fix it, literally. Play with it, make sure it was right, back out some, advance. So by the time that Go 1 happened, we had scrubbed the language clean to the best of our knowledge. Turned out we missed a few things, but it was an interesting process because of the complete automation with which we were able to update not only our code, but everybody else's code while doing that. And it got used one more important time later. We decided to change the API that was used in Go for protocol buffers, which are used on every third line of every Google source file out there. And we want to change the API. And we wrote a GoFix module to do this. And in literally one command, updated the entire tree of Go programs to use the new API, retired the old API at a stroke, and we were done. And so this is an interesting comparison to other stories about trying to change protocol buffer APIs and how hard that's been over the massive code base that's there. So I agree completely with what Bjorn is saying, that a lot of this is actually automatable if you're willing to have the courage to clean up, stick to your guns, and really get rid of the old stuff.
I want to step back a little bit to the original question, or some other aspect of the original question that we kind of lost, I think, which was, okay, is this too much to keep in your head? And can, especially I think when you have a richer type system was kind of one of your main examples, right? Like the examples I was giving of ownership and borrowing and everything. And I think there's an interesting trade-off here, because it is true, of course, that like a language like Rust will kind of push you in a direction where you have to learn up front and learn these certain patterns up front and select which one to use. And there is a certain amount of overhead associated with that. On the other hand, if you just have, say, pointer, like in Java or C# or something like that, I would argue that a lot of times you still have these patterns there, right? There is still ownership, especially when there's mutability or resources. There is ownership, there is borrowing. It's all in the code. It's just implicit. It's not written down, and it may not have been thought about as carefully as it should have been. So I've heard from a number of people now, actually, who were learning systems programming for the first time, who were too afraid to use C or just never had the time or whatever, and they've come to use Rust, and they found that there is some upfront learning, but it's helpful to them as compared to their attempts to learn C, because they are sort of guided down channels. They say, we suggest this is the proper way to manage your resources. You should have a single owner. That's kind of a lesson that you end up learning by virtue of double freeing too much in C code, right? And having similar problems. So I'm not sure how much of the complexity is in the languages and how much I guess I am pretty sure, actually. I take that back. I feel that most of the complexity is in the domain. And exposing it at the language level is not a mistake in that regard.
Dave, you should know you're my academic grandfather. Craig Chambers has been my advisor through my master's. So it's a great honor to see. I wanted to shake your hand, but I was like, what the hell am I going to say that's going to be interesting to him? So kind of I'll continue answering sort of the higher level question, which is, why do I have to keep all this detail in my mind? I'm sure you're thinking of things like self and small talk, which are so fluid and so easy to kind of experiment with, and right. In my opinion, just the same as Nikos, I think it's a lot of it is inherent. Systems languages have this extra burden on top of everything, which is, well, you got to worry about at the same time the cathedral, the bricks, and the molecules in the bricks, and that's the way it is. It's pretty much cut and dried. And the way you can build larger bricks, smaller bricks, nicer molecules, better molecules, whatnot. Prefabricated, whatever. You can layer things any way you want, but at the end of the day, you're going to have to worry the whole gamut of scale there. So to a good extent, it's cut and dried. That said, of course, different languages try to kind of carve the space saliently, things like garbage collection, it's just simplify a ton of things. Like Rob said, we're not going to even worry about this kind of stuff. We're going to just let the garbage collector. At the same time, we just did some experimentation at Facebook, and, it was like a good, for the same payload, the program would consume like 3 times as much memory in the garbage collection versus the eagerly managed version. So we just can't afford it. And in terms of efficiency, when you talk about the razor-thin margins, every percent you gain in a core component at a server level is going to mean like literally millions of dollars annually in terms of power costs alone, not to mention disks failing and memory failing and all the equipment replacement. So essentially, we're looking at things that probably for a researcher that simply don't make sense. They're not a concern. They're not part of the thing they worry about. But for us, if kind of interest, glorious cost is going to reduce to 0.5% efficiency. So it's going to reduce efficiency. Okay, double negation there. You see what I mean, right? If it's going to increase efficiency just by a thin margin, it's going to be like there's going to be a good money in it, and there's going to be like a very good payoff in that, and people are going to just accept it. And I think at some point there's going to be a reality that it's a large system. I mean, we're talking about large systems, however, written in languages that aspire at allowing that kind of control. And at some point, there's got to be all that complexity laying around.
Okay. I just wanted to say the same thing as Andre, just a lot of these things. And there's a time scale difference among. But I think I would like to push back on this thing that you just want to have it, not remember these things in your head, just write down what you want in your head. I hear often people want programming to be as easy as writing in English. And the problem is English is horribly imprecise. And I find to my great embarrassment that I've said something perfectly clearly in English, I understood it, and then everybody else understands something else. And I would like to emphasize Nico's point is that if things in interfaces are more precisely specified in types with constraints, with requirements and such, you get more stable interfaces, you get more things caught, and you get better communication between different groups. The classical example is a Mars climate orbiter. There was nothing wrong with the type system, there was nothing wrong with the code, but it was a trivial type system. A double is a double, whether it is MKS or the imperial system, and we just lost a $600 million probe. I think for the kind of applications I think of most and care about most, like the brakes on my car and such, I would rather see it done at a technical level than an intuitive level. I hope I didn't caricature you too much. Okay, then.
Oh, thank you so much. I mean, of course, there are different domains and things, and if any combination of language features is sufficient to make sure the brakes work on my car well enough compared to putting that same amount of effort into testing and fault injection and all of those things, I'm not aware of it, but you all may be. If Facebook cost me twice as much to join, I wouldn't mind. But I don't know what your costs are for the some of the bugs you might have for not having automatic reclamation. I observe that Google has gone with Go, the automatic reclamation algorithm. The experience I have all the time is I have a really neat idea in my head because that's what I value for something to build. And I feel like when I build it in most languages, I am slowed down so much by this stuff I have to carry in my head. It's really hard to hold on to that shining idea. Randy Smith has said about the alternate reality kit, which is one of my shining things, that if he had to do it in anything but Smalltalk, he wouldn't have gotten the first 3 lines of code written. Now, I know that if you're writing something that has been written a million times before, and maybe you're sending it to Mars or something, sure, all the help you can get is worthwhile. But I would love to be able to create things that run reasonably fast, and maybe later on I can put in all this stuff to get a little extra security, but it would sure be nice if I could try out that idea, and maybe this is just my own weird personality, try out that idea so easily, not have to rewrite it. And that's where I was coming from with my question. So thank you for letting me rebut.
Oh, are you kidding me? Come on. So do you want to retort his retort? Okay. What would you call that?
A re-retort? I don't know. No, I just want to make a point about garbage collection because when we did, and I also should say not everything at Google is written in Go, and a lot of it shouldn't be because of issues like garbage collection latency. Some of the core stuff needs to be written in exactly these sort of what I think of as lower level or at least more precise descriptions of behaviors. But there are 2 points about garbage collection that I think are often lost on the systems programming community, given the pushback I used to get. I don't get so much anymore. One is that we don't claim that it's the right solution for everything, but it is a right solution for an awful lot of stuff. And for those things, I shouldn't need to pay the price that I have to pay for the low-level things. This was the point that drove us to create Go in the first place. C++ is probably the right choice for a lot of the code at Google, but not all of it, and not even, maybe even the majority of it. A language that's easier to use, and memory management being one of the most important parts of that, is actually valid to have around. The other point is garbage collection is not intrinsically slow. It's an idea. We don't have the best garbage collection in the world. I think we have a good one, but it's not the best. We hope to have a great one. We're working hard on trying to make a good one. But the point is that what is often, it's a bit like what I was saying about threads. When people complain about garbage collection, they're complaining about a certain style of garbage collection. There's ways to garbage collect that don't have those costs. They have other issues, but performance isn't necessarily made worse. Arenas aren't necessarily made bigger. It's just how it's implemented. And you have to implement it. You've got to get it right. But garbage collection is an idea. It's not a performance problem. It's something else. I just get tired of people complaining about garbage collection when you think of how much better the APIs look when you don't have to worry about the questions of who owns what and so on. And this is not meant to slag off Rust, who I think is taking a really fascinating angle on how to deal with this. But the APIs in a typical Go program are half the complexity of a C++ equivalent because you don't have to talk about the memory management. And that makes the program smaller, simpler, easier to understand, and you have less to carry in your head as a result. So I'm completely sympathetic to the point you're making. Anyone? Who's going to pick on garbage collection?
So I don't want to pick on garbage collection, but I want to say a couple things. One, one of the things that Bjarne said this morning that really stuck with me was was kind of busting various myths, right? And one of them was people want an efficient language, and he said no, they don't, not most of the time, right? They just need it sometimes, And a lot of the times you don't care. And I kind of feel like that's what I'm hearing from you, which is saying, I don't need the utmost of efficiency. I don't need to examine every assembly language instruction all the time. And a lot of times I have this nice idea and I want to write it out and see it run reasonably fast. And maybe later I can go tune it when I do care. And I'm completely sympathetic to that. And I think it's tricky when you're marketing a language, I have to say, because you want to emphasize the things that your language does best, right? And I think what Rust does really well, and what I hope that we will do better than anybody else, is writing really efficient, really safe code that brings those two things together. I also want to see us do really inefficient code really well, right? I want to see it really nice to write convenient code where you don't care if you copy that memory 2 times or 3 times, or you don't care so much if you have a garbage collector exactly when it's going to be freed. Like, one of the things I didn't talk about is that we're working on an optional garbage collection strategy, for example, that you can opt into. You can say, as one of those different ownership strategies, one might be GC'd. Right? And that just, it's hard. Combining especially GC and non-GC is a tricky problem. So that's taking us time. But I think there's a big range, and I would really like to see that it's easy to write inefficient and it's easy to make it more efficient. And when you need it to be efficient from the start, that's fine. We have the tools there for you there too. Right?
I'm all in favor of what you said in terms of we need all the help we can get. And as you said, maybe it's just me, so I'll say maybe it's just me, but expressing interfaces in terms of type systems and tighter types actually help me think. And I find that my great bright idea that I started out with has flaws. And running examples gets me my errors shown to me good and hard, and getting a type system put up in front, static type system, gets it even faster and forces me to think. So I actually think of the type system as my first line of defense against my own sloppy thinking.
I think this is getting real close to dynamic typing versus static typing kind of debate. Just saying, it's a matter in which reasonable people are known to disagree.
Right. Well, I'm not going to disagree. I'm just going to say that I had a bit of an epiphany last year when I realized that the reason that unit testing was being driven by the dynamic language people was that they had that instead of static typing. Yeah. I never really put 2 and 2 together.
That wasn't funny. It's a fact, right?
All right, so great. Let's start doing a quick question and answer.
So this is kind of going back to what David was talking about a little bit, but maybe not to the extreme way. One thing is that we can equate money to is how much money it costs to facilitate change. And this directly relates to application binary versioning, right? And one of the things that I was really inspired by with David's work many, many years ago was how easy it was to facilitate change. So if you look at what that implies, one way to look at it is a typing argument, right? But the other way to look at it is are there ways of changing code post-release without breaking client code? And a lot of people talk about interfaces, but that's one part of it. But if you look out at the layout in memory of how the objects are laid out, right? It's the this pointer is always implicit in the C++ layout, whereas in the work of David, it was you could pass it and change your identity. Now, I'm not necessarily saying that you want extreme changeability, but maybe in terms of that, I think that is a legitimate issue that has money associated with it, because if every time you change your libraries, you break somebody else in your top to bottom stack, this is a big problem. Why isn't there more emphasis in the language community on mechanisms directly designed to facilitate change or programming in the large?
Rob, how about you, man?
I'm not sure I have an on-point answer, but when I was working at AT&T, which is when Bjarne was working at AT&T, the big moneymaker was the 5 ESS data switch, local machine. It was basically a VAX scale machine with lots of redundancy that gives you dial tone and did your dialing for you. And every one of those that was installed was different because there were patches that went out and different people put in different patches, right? The French ones wouldn't put in the Spanish language patch for the Spanish dialing plan. And so somehow, and I have no idea how, those guys then, which was like the 80s, managed to make an environment that they could monkey patch remotely in binary all the time. And I like your question because I've been thinking lately, how the hell did they do that? How did the phones keep working while all of them were being patched dynamically? Maybe Bjarne remembers and knows more about it.
I remember a little bit about it, but I don't want to go there just now. What I want is to give my answer to what you have. There's a huge chunk of the language community that's been working along your lines and along your thinking forever. And it just isn't my world. I'm much more interested in getting the telephone switches and the brakes and the Mars probes and the web servers reliable and efficient. That's my domain. On my first slide, it said no one language is good enough for everybody and everything. And I think that you find quite a few languages that's highly dynamic, highly flexible. The generation of languages starting with Lisp and Smalltalk, they have never been out of fashion, and they have never had no support. It just isn't what I'm talking about.
Bjarne and I as a duo would be really boring because we kind of repeat each other. Yeah, I mean, essentially, here's the way I see it. At Facebook, we release the entire Facebook site like twice a week, which is quite a performance when you consider like with this an unspecified number but large of machines, and there's a lot of interacting libraries, a lot of interacting things. And, essentially, exactly, it's not the business we're in, and I'll explain exactly what I mean by that. So, by means of introduction, I mean, we resolve the same problem through different means. We have, upload system, BitTorrent, what have you, and we have a system to kind of wind down the existing executable, install the new one, put into run, and etc. Warm things up. It's a kind of complex but a very well functioning system. But what I mean to say, we're not in that business because, and I'll tell you exactly experiments. So I've been working for months on our core PHP compiler team, which is essentially like any change in that compiler, the performance of the code generated by that compiler is going to impact the bottom line of Facebook significantly. And it's the way you achieve hot patching is by indirection. So essentially, you add some indirection into the mix, and you have pointers, and you follow things, and essentially kind of patch things at the right level, and so on. So there's more indirections in the mix, meaning instead of arrays, you're gonna have lists, trees, indirect pointers, and at that point, we're kind of whoa, because arrays are it. I mean, kind of stop there, full stop. Arrays are it, right? Because, and I'm not talking arrays. I'm talking like structs. Kind of struct is like a little array that's heterogeneous, and I'm not talking even about structs. I'm talking about the first cache line in the structs, because if you swap two fields in a struct, you got like 2% drop in performance. The first cache line in the struct is where it's hot. That's where it happens. That's where the rubber hits the road. And if you come and say, oh, we need hot patching, and I'm like, oh, that's going to totally ruin my first line of cache right there, and I'm going to die, right? So as Bjarne said, it's not the business we're in. And I'm not saying people shouldn't work on that. I'm just saying, we can't afford to work on that.
Yeah, you pretty much said what I wanted to say, actually, only more colorfully, so I'll leave it there.
So to expand that a little further, I think there's a pattern that like Erlang exemplifies, but I think people are starting to recognize more now, which is like fail quickly and restart fast. If you can do that incrementally, like take a server down, bring it up again, and not miss any traffic as a result, you can do that in a way that boots the new system up right away. And it's actually a lot easier to follow that pattern as a design principle than to try to invent ways to dynamically update stuff while it's running. Modern machines can start up a new server in a matter of milliseconds. Why bother with all the patching?
You also kind of said what I want to say, but I'm going to repeat it too. The other thing I wanted to add is just that I think this kind of restart and monkey patching is extremely semantically challenging. Like, in other words, it really will depend. The right way to plug in new code is one thing. That costs some vtables, it costs some other things. But to update the existing data, and especially if the layout has changed or changed meaning, maybe it's always been 2 integers, but now it's Cartesian, and now then it's polar coordinates, or I don't know, something else. Like, these kind of changes are pretty hard. So I think it's better off, in terms of, for a lot of systems at least, you're better off trying to draw boundaries along the way that Erlang and other systems have done, and say, we're going to fail by bringing this down and bringing it back up, and we're going to have a model for what is persistent and what is not that's already there for lots of other reasons that will help us to bridge this gap. And trying to fully automate it is going to be very challenging, I think.
So that was a short question, short answer.
Very short, and I actually remembered part of what Rob asked. The main ideas for being able to patch the data structures and the switches is that you deploy them with data structures that's slightly too big and with jump tables that are slightly too big, so that if nothing else, you can always have a thing that says switch to the new one for a while. And you must not just ship what fits your current system. Always fits two sizes larger. And then I'm going to cut.
All right, so you had a question, then you had a question.
I've got 3 questions, but I'll only ask one of them. So if you have 3 answers, please only give one of them. I guess my question would be, I work mostly with C++, and one thing that we've noticed is that compile times take forever and link times take forever, largely because you have all of these type system-y things. Like, we do a lot of static analysis sort of moves into the type system. You have a lot of entities, and it takes a long time to deal with all of them. Is this only a problem for C++? Do other languages have the problem? Your particular languages have the problem, and if not, why not? And what is it for C++? What is the future of that?
Great question.
It's a major problem, but C++ is certainly not the only one. If you wanted really interesting, try Scala. But what you said there about the causes of it, unless you're into weird template metaprogramming, the entities in your program are not the real problem. It's the fact that we recompile the header files hundreds of times. And this problem is getting unmanageable, and even the standards committee has noticed it. And I'm going and I'm going to spend some significant time on it in 3 weeks. We will see. Standards committees don't work fast, and they are not good at coming up at the simplest, most straightforward solution. But the problem is not unnoticed, and I see no reason why we couldn't be 10 times faster.
I guess we can go down. I actually don't know whether this is a problem in Rust or not, because the Rust compiler isn't screaming fast, but we also have spent 0 time optimizing it. So it's hard to say. I know that we avoided this C++ problem by the fact that we parse an entire set of compilation unit at a time, not one file, but the whole tree, and that lets us avoid reparsing and everything else. And I know also that when we build C++, that's what we do now too in Mozilla. We concatenate all the files into one big file and build that, because that also is much faster. So at least that's part of the problem, or part of the solution. But yeah, there is a price.
Yeah, so they say the Rust compiler ain't that fast, is it? I heard bad mouths, saying it.
I will say one other thing, which is that when you build Rust, it's building itself, and then it's building itself with the version of itself that it built, and it's also building all the standard libraries. So a lot of people say, "Oh, it takes a long time to run make," and that is true, but it's building everything 3 times. So
So these are Rust programs. But anyhow, getting back to the question, Well, here's the thing. I think it's a problem that's intrinsic to C++. And it's a problem intrinsic to C++ because it's a problem intrinsic to C. And C++, because of the templates that Björn mentioned, adds to it. The problem with C was it was designed for a batch compilation system. I'm not sure if many of you even know the backslash. Does anyone know why the backslash termination line was ever introduced? Because it was run through a preprocessor that only did that because there's not enough memory for the whole thing to kind of, the preprocessing and the compilation and everything. So you run the C program through the guy that eliminates the backslashes. And then you run the guy through the guy that does digraphs and trigraphs. And then you run the program through the guy, at least in theory. And then compilers kind of quickly modernized and did all the processing at once. But essentially it was the whole language, C language, was designed with such batch multi-stage processing in mind. And it shows, and the way it shows is that every character, the meaning of every token in C and C++ depends on pretty much everything that's before it, and it's completely serial in nature. We've thrown, like Rob also said, essentially like also what I call like high traffic companies like Google, Facebook, Amazon, and others. They share the same problem. They have a huge C++ code base, and they have a comparatively huge army of computers and an army of engineers, the most senior engineers they can muster, to kind of babysit the build system. And we've been throwing at it like all intelligence and all kind of smarts we could. And at the end of the day, it was an unsolvable problem. It just takes so long to take from the source code to the binaries. And actually, people came to me to say, first they said, oh, why don't you go play with D and kind of do something? And I played with it for 6 months, and nice things happened. And then they came, oh, that's pretty cool. And actually, I noticed it compiles real fast. So we don't know what to do anymore. We're at the end of our wits, and we noticed that this other language compiles so much faster. So it turns out its speed of compilation that cannot be obtained with any money for C++. There's no amount of money that you could pay someone to compile code as fast as D does. And that was a winner. That was like, oh, so we're going to try this other language and see what the hell happens. So it's a problem that's intrinsic to C++ for historical reasons. I'm sure there's knowledge that there's work on modules going on and more, but fundamentally it remains the case that for most extant code and tools, this is an issue.
Yeah, I actually have some numbers on this, but I can't remember them precisely. They're in the splash talk I cited. We measured how much data went to the compiler for a large C++ build at Google. I don't remember it exactly, but I think it was something like 4.2 million bytes per byte of input source meet the compiler. It was a 1 million factor blow up in the amount of source that the compiler actually looked at because of the header inclusion problem. I don't think it has anything to do with templates. I think it has to do with putting a class per header file. I think that's really where the problem starts. It's a huge, huge problem. And modules are, I hope, really going to fix it and will make a profound effect on the compilability speed of C++. I really hope so.
The reason I take this mic back is mostly to say that I don't disagree with that. This is a major problem. It's a growing problem. It needs to be dealt with. And I am not sort of totally rah-rah optimistic, but I think it'll probably be solved.
Cool. His hand up was earlier, man.
Okay, so I'm coming from the background of somebody who does most of my work in C++ as well, but my question is related to the decision to not consider ABIs as part of language specification, and whether, for Bjarne, whether you regret that at all, and for the rest of you, what your thoughts in developing your languages were with regard to specifying the binary interfaces or specifying requirements for the binary interfaces, within the limits of portability, and the motivations for that.
Thanks.
Yes, it would have been really nice if there was binary interfaces defined for C++. It wasn't, because it was seen as beyond the scope of the standards committee, just as it was beyond the scope of the standards committee for C. But C was very lucky. Each platform had a de facto owner and a de facto standard for ABI, and people used this, including the C++ guys. The reason C++ didn't get one of those was that essentially everybody thought they could own C++ on the platform. And so you had GNU, Microsoft, and Borland and Sortec, each defining their ABI, carefully making sure you couldn't link to the enemy's code. And each time we tried to solve this, we've run into the two problems. One, it is not considered part of the standards committee's charter. And two, people have always been more keen on being compatible with their existing users than to break all their code to be compatible with everybody else. There are some hope in the 64-bit ABIs and the Itanium ABI, and I hope people will get their act together, but I'm not holding my breath.
So we've given some thought to this. And one of the things we have done is made it possible to specify. So Rust has a kind of model very similar to C. So you can essentially opt into saying, I want this representation to be the standard C representation. And there's a sort of well-defined meaning for that. And you can say, I want this function to be callable from C and so forth. And they're completely interoperable in that way, which is very nice when using FFIs and so forth. We've tried to reserve for ourselves the right to optimize representations beyond that. So, for example, well, you can have, I don't know, it's not worth going into details, but we can sometimes omit words and pack away things that would be harder to do if we were forcing ourselves to always follow the same rules. So there's a little bit of a tension there between wanting to do the best optimizations you can, given the target platform and everything else, and wanting to reserve the right to change that in the future when you think of something clever that you didn't think of when you wrote the spec, and wanting to ensure total binary compatibility across all time. So I don't know. It's an interesting question.
So just to make sure I understood the question, so you're talking about ABI, in defining an ABI inside the language and or with communicating with other languages, both? Right. Okay, so I'm going to kind of...
Within the language was my primary question.
You need two compilers to have that problem.
Right. So, yeah, you know... actually, so there's... okay, so there's two... You know what? Let me answer the question I wish you'd asked, okay? So, let me reframe it. So I'm going to say, well, what's the deal with ABI? Do you want to specify the language very precisely at the binary level, thus encouraging two compilers or more? And the second thing, which I'm going to add liberally from my own hat, is, what's the deal with interoperating with other languages and so on and so forth? For the three of us, I think it's nice because we're kind of new kids on the block, and C++ and C are kind of the established ABI standards. So for our part, D tries to kind of interoperate well with C and C++, and there's external C and external C++. We're introducing support for namespaces. Again, use function calls from namespaces. It's a mangling issue, as well as some, a bit of an ABI issue because STD is special in GNU and stuff like that. But anyhow, so, as far as other languages are concerned, it's nice to play well with the incumbent for obvious reasons. Within the language, I think it's nice to give people, code writers, a sense of what they're doing, because layout control is a huge performance has a huge performance benefit. So it's nice when people write a struct to know that their fields are not going to be sorted by name or something in the final binary, right? That would be stupid, right? And because of that, it's nice to have some level of guarantees, but at the same time, it's also nice to give the compiler writer some freedom. And the way we went in D was, I think it's reasonable. Like whenever you have a struct, it looks like it's pretty much C rules, and whenever you have a class, which is like kind of reference access, kind of a bit more isolated and everything, the compiler has a lot more freedom to rearrange fields. This is very similar to what C++ does, which is as soon as you have a virtual in the mix, the compiler has a lot more freedom to kind of rearrange the fields and kind of play with things, because it assumes people are going to access it through the virtual functions and such. So I think we're in good shape, and I think it's an interesting problem. And I think as a bottom rule, a new language should play well with the existing languages on the platforms.
So with Go, we only worried about this as an issue at all when talking to C or C++, because there you're forced to face it. And it's actually one of the hardest things to work on, because every platform has its own rules and we have to encode them, and it's all quite unpleasant, but we did the work because it was necessary. For Go itself, we actually deliberately don't worry about it. The compiler's fast enough. The entire library builds on my laptop in 6 seconds. Everything's done from source. So we actually require that all the stuff you're bringing into the binary be built by the same version of the compiler. And just therefore it doesn't matter. Whatever that compiler thinks is right is right. Yes, we're giving up some freedom for control of memory, although there are actually pretty good rules. You can do a good job. But we're also freeing ourselves from having to worry too much about it.
All right, well, thanks to the panel. Awesome. And thanks for all the great questions. We have to go drink beer now. Sorry, man. I know you hate that, Bjarne.